Hello everyone. So today I'm going to present to you the ring of charge diagram in our setup for solving the integral of a ring of charge. So let's just get straight into it. You have to imagine before in 3D what this looks like. So you'll have a ring, looks like this, and then in your ring you'll have some sort of stick, I guess if you will, with a point on the stick. The stick is imaginary, but there's a point out here, and then all of your energy is going to that point, all the energy. So in 2D space, if you will, we have our ring, and then our point P right here. We have our radius of the circle, and then our distance from the radius to the point called Z. Then we have each little derivative of the charge going to the point, which gives us some sort of little energy. And we have A, which is, this hypotenuse length. So some things to know, some variables. Our purpose for solving is to add up all the EX's. That's how we'll get our, final results. Our radius obviously equals the radius. Our hypotenuse is equal to the radius squared plus our distance to the point squared under our square roots. Our cosine theta, sorry this doesn't look too great, obviously equals to the adjacent Z over the hypotenuse, which is, you can see there. And one common question that I guess the general public had was, why are we just adding up all the EX's and not total E? Well, I have the solution. The EY's cancel out. If you see here, this EY and this EY, one's positive, one's negative, they cancel. And that's about it. Basic.
Hello, this is the second part of the derivation. So as you see here, we have the general equation for the electric field. Now, my compadre Alex is going to show you how to substitute these babies in here. But we have KQ over A squared, and remember, A is that distance from the point to the ring, okay? That's what A is. And then we also have cosine theta because we don't care about the y direction, we only care about, I'm sorry, I got confused. We do care, is it the X or the Y direction?
The X.
X direction, yeah, I'm so sorry about that. We care about the X, so here it is right here. Now, Alex will come in to substitute stuff in for Q and for A. Alex?
Answer your question.
Oh, and to answer the question, why do we use lambda? Well, because, as you can see, we're gonna have to integrate this later, but we can't integrate with Q. That's why we need lambda, so we can express Q in a different way. So lambda is just the linear charge density, so it's the charge density. So as you can see here, we can write it like this. So lambda is Q over L, which again is the charge density. And we can solve for Q to allow us to substitute it in later. So that's why we have lambda. Now Alex, welcome to the video.
Okay, so now we're going to plug in everything we found into our equation. So our A was square root of r squared plus z squared. So when we sub that in here, it just becomes r squared plus z squared because we get rid of the square root sign. And then cosine theta becomes what we found earlier, which was z over r square root of r squared plus z squared. And that, when you multiply these two together, you get kqz over r squared plus z squared to the 3/2 because we combined the r squared plus z squared to the first power and the r squared plus z squared to the 1/2 power. And when we multiply bases, we combine the exponents, we add them, so it becomes 3/2. And then we can substitute the q that Jack showed us how to find, and that's how we get our final answer.
Alright, so the next part of this is we're going to actually take the integral of the electric field to find the force. So, to take the integral, we're going to be using this equation up here. And since most of these are just constants, we can actually take them out of the integral. That being k, z, lambda, radius, z, and all the powers, which just leaves us with d theta. And we're taking that from 0 to 2 pi because that's the complete circumference of the circle. Okay, to answer the question, why do we use an integral and why do we evaluate it? The integral just means that we're taking each little piece of the ring and finding the electric force within that little piece. And we're evaluating it because we want the entire ring, not just one singular piece. So we take it from the entire circumference of the ring 0 to 2 pi.
Alrighty, hi pals. To wrap things up, as Emma was saying, we're evaluating from 0 to 2 pi out of this equation because we're trying to find the electric field from point P along the z-axis, so to there. So when we do that, the equation we end up with is k2q over c squared plus r squared to the 3/2 power, and this essentially, when you plug in all the numerals and whatnot, will give you your electric field strength. So a question that people will ask is, why do we use phi and not theta? As Emma accidentally said in the previous portion of the video. Well, the reason why we're using phi is because since we're valuing from 0 to 2 pi, that is around the ring, and the ring is essentially located on the x and y axis. The point of using the z-axis is to make the connection to the point. Therefore, instead of using theta, which is connecting the z and the y-axis, we use phi, which connects the y and the x-axis. And yeah, that's pretty much it. Thank you for watching this video on finding the electric field for a ring of charge. Love that.